everyone, this is the 30th video in the Mathematical Methods for Economics series, and this video is about what is known as the Taylor's formula. To give you some background, in the previous video, which you can find on the CEC playlist, and we've also provided the link for the two parts to this video in the description box, we covered polynomial approximations to a function. We talked about linear approximations, quadratic approximations, and even higher order polynomial approximations to a given function. In particular, if you look here on this slide, the nth order Taylor polynomial approximation of the function f of x around the point x equal to a is given by the following expression, where the function f of x is approximated by this polynomial f of a plus f prime at a times x minus a plus 1 by 2 factorial f double prime at a times x minus a the whole squared, and so on till 1 by n factorial, the nth derivative of the function at a times x minus a to the power n. And if we take this approximation around x equal to 0, which is what our lecture today is going to mainly focus on entirely in fact, is so if we take this approximation around x equal to 0, which is also called the Maclaurin's polynomial approximation, then f of x is approximated by f of 0 plus f prime at 0, the first derivative of the function at 0 times x plus 1 by 2 factorial f double prime at 0 times x squared plus and so on till 1 by n factorial, the nth derivative of the function at 0 times x to the power n. So you can clearly see a pattern here in the terms here, and this formula should be easy to remember. Now, what is this video all about? The question that we are asking in this video is, we have an approximation here, and the question we are asking is, how good is this approximation? Whether we are taking the approximation around 0, like in this case on this slide or in the previous slide around x equal to a, that does not matter. The point is that we have an approximation here, and how far off the mark are we? And if we are off the mark, then to what extent are we off the mark? So, this is what we are trying to get at. Let us get a sense of things. So, if I take x equal to 0, for example, in this particular case here, where I am taking the approximation around x equal to 0, then you can see that there is no error. You can see that the left hand side will be exactly equal to the right hand side. The left hand side, because we are evaluating this at x equal to 0, so the left hand side would be f of 0, the right hand side would be f of 0, and all the other terms will vanish because x is equal to 0. So, at x equal to 0, there is no error. The left hand side is exactly equal to the right hand side. However, if x is not equal to 0, then it is not necessary that the left hand side and the right hand side will necessarily be the same. So, in this case, we want to ask ourselves, what exactly is the error that we are making in the polynomial approximation that we are taking? And if you have been students of science, then this is something, the idea of reporting the error, especially when you are writing out the results of your experiments, that must be totally something that you can relate to. So, the point here is, we are asking ourselves, what can we say about the error that we are making in the approximation, and how do we estimate that? So, how do we arrive at an expression for that? So, in particular, what we can do is, to incorporate this error, we can write the function f of x exactly equal to the polynomial approximation, which starts from this expression here, f of 0 plus f prime at 0 times x plus 1 by 2 factorial f double prime at 0 times x squared, and so on till 1 by n factorial, the nth derivative at 0 times x to the power n. And now if you notice here, I have introduced what is the error that I have made, or what we call here the remainder term. Another way of looking at the remainder is that it can be seen as a difference between the true value of the function, which is given by the left hand side, and the polynomial approximation, the approximated value, the estimated value which is given by the polynomial approximation here. So, r n plus 1 of x is what represents the remainder. 2 points about this. One, that the error can be negative or positive. So, if the left hand side and the polynomial approximation, they differ, they may the difference between the true value and the estimated value may be negative or positive. But in this context, unless it is needed, we can simply focus on the absolute value of the error. We do not have to care about the sign here. So, we will focus on the absolute value of the error. The other point I want to make here before I give you the expression for this error is that this remainder, the error or the remainder is represented by r n plus 1 of x. So, we are basically trying to say here that the remainder depends on two things. One is the value of x that we are taking, and the second is the n or the value of n or the order of the approximation that we are taking. So, this will become clearer in the next slide, where I am now going to introduce the expression for the remainder, which is also known as the Lagrange's form of the remainder. So, the remainder term here, r n plus 1 of x, is given by 1 divided by n plus 1 factorial times the n plus 1th derivative of the function. But now there is a difference. The n plus 1th derivative is not evaluated as 0, it is evaluated at a number c which is between 0 and x. And this n plus 1th derivative times x to the power n plus 1. Here also there is a pattern, because if you remember, when we were taking the polynomial approximation, the nth order polynomial approximation, the last term was 1 by n factorial times the nth derivative of the function at 0 times x to the power n. So, this term follows naturally from that last term, because you are just kind of taking the next term, except that the n plus 1th derivative is evaluated at c. We will also, if time permits, towards the end of this talk, we will bring in the proof of the Lagrange's form of the remainder. The other thing that you have to notice here is that if you are taking the n plus 1th derivative, then the function should be n plus 1 times differentiable in an interval including 0 and x. So, that is one of the assumptions that we are making, that the function is n plus 1 times differentiable, and this then is a remainder for the polynomial expression, for the estimation that we are conducting. So, if we now incorporate this remainder into the function, so if we substitute this expression for r n plus 1 of x, this then gives us the Taylor's formula. So, here it enters your Taylor's formula, which is the focus of our discussion today. So, that f of x is exactly now equal to f of 0 plus f prime at 0 times x plus 1 by 2 factorial f double prime at 0 times x squared and so on till the nth term, plus the remainder term, which is now 1 divided by n plus 1 factorial times the n plus 1th derivative of the function evaluated at c times x to the power n plus 1. So, this is something you must note here, that the n plus 1th derivative is evaluated at c for some number c between 0 and x. Just as an aside, because sometimes you may be dealing with approximations around x equal to a in general, not necessarily x equal to 0 in particular. So, in that case, the only difference is that the remainder term is the same, except that now instead of x to the power n plus 1, you have x minus a to the power n plus 1, and c now is some number between x and a. So, just take note of this, otherwise everything remains the same. Okay. So, the Taylor's formula is what we have already talked about, we have introduced, and let us get a sense of things. To do that, let us suppose n is equal to 1, which is to say that we are taking the linear approximation. So, if n is equal to 1, n always refers, please note here, n refers to the polynomial, the order of the polynomial approximation. So, if n is equal to 1, then f of x is approximately equal to f of 0 plus f prime at 0 times x, it is a linear approximation, and the Taylor's formula will then be given by f of 0 plus f prime at 0 times x plus 1 by 2 factorial, the second derivative at c times x squared. So, hope you've got the drift and you've got a sense of how you're going to be using this formula. And the other thing which is very important here, because this is something you'll be doing, this is an exercise you'll be carrying out for practically every problem that we do in this video, is that what is the upper limit for the error? So, if you look at this expression for r n plus 1 of x, this once you calculate, you'll be given a particular point which is x, or you'll be given, you'll be starting with a particular order of the approximation. Basically, the end result is that you will get an expression for r which is in terms of c. So, you might be, because it's in terms of c, it's a function of c, you want to understand what exactly is the error that you're making. Now, because you may not get a precise number, it will, because the error will be in terms of c, you might want to look at the upper limit for the error, because this would be a good way of understanding what is the maximum mistake you're making. So, if we want to look at the upper limit for the error, then let's suppose, because for the upper limit, let's suppose the n plus 1th derivative at c, again we will take the absolute value of this, because ultimately we are interested in the absolute value of the error. Let's suppose this n plus 1th derivative at c is at most m. Okay. So, in that case, because the order of the approximation is given to us and the value of x is given to us, so then r of n plus 1 of x is less than or equal to the upper limit of the n plus 1th derivative, which is m, divided by n plus 1 factorial times the absolute value of x to the power n plus 1. Okay. And if you notice the way the terms are arranged here, you can clearly see that the higher the order of the approximation, the higher the n, the smaller would be the error. Similarly, the closer x is to 0, and in particular if x mod x lies, if mod x is less than or equal to 1, the smaller your error would be, because then only you will be able to constrain x to values between 0 and 1, or between minus 0 and minus 0.1. So, in that case, then only when you take the powers, the numbers will successively become smaller, so that you can get a smaller and smaller error. So, you would like to have as high as possible the order of the approximation, and x should be as close to 0 as possible. With this, let us look at this example that I have here on this slide, and let's check how well we've grasped the concepts so far. The question here asks you to find the Taylor's formula for the function f of x equal to square root of x plus 36, which for convenience I am writing as x plus 36 to the power half, because that makes it easier to evaluate the derivatives. And let's take the order of approximation as 1. So, n is equal to 1, which is to say that we are taking a linear approximation. Then you have to find the Taylor's formula in part B to get an estimate. You have to find the Taylor's formula in part A and use the Taylor's approximation that you get from part A to get an estimate of square root of 36.03, and also report the error as well as its upper bound. So, let's see how these calculations are done. Let's look at the first part. Our function is given by x plus 36 to the power half. The Taylor's formula here, because n is equal to 1, will go up till 1 by 2 factorial for the error terms, because error term has 1 by n plus 1 factorial. So, that will be our last term here for the Taylor's formula. Therefore, f of x is equal to f of 0 plus f prime at 0 times x plus 1 by 2 factorial, the second derivative at c times x squared. Okay. So, let's do the groundwork before we plug in the results into this equation here. So, we know that f of 0 here will be square root of 36, which is 6. F prime of x would be half x plus 36 to the power minus half. So, that f prime at 0 will be 1 by 12. F double prime of x is minus 1 by 4 x plus 36 to the power minus 3 by 2. So, that the second derivative, now remember, because the second derivative is evaluated at c, this is given by minus 1 by 4, excuse me, there is a typo here, it is c plus 36 to the power minus 3 by 2. So, our function here, the Taylor's formula is given by f of x equal to 6 plus 1 by 12 minus, because there is a 1 by 2 here, so 1 by 2 times 1 by 4, so that is 1 by 8, c plus 36 to the power minus 3 by 2 times x squared. Let us now use the result that we obtained in part A to obtain an estimate for square root of 36.03. Here you can see that x is 0.03. If you plug 0.03 into the function here, you will get 36.03. So, clearly x is close to 0 and we should get a good approximation here. Now, if you notice here from part A, the Taylor's formula f of x, we just have to take the approximation part now, which is 6 plus 1 by 12 times x, right. So, just substitute for the value of x. We do not have to put in the remainder term here, because right now we want an estimate for the square root of 36.03. So, we will just take the polynomial approximation, the linear approximation, which is 6 plus 1 by 12 times x. And now, once you substitute for x, which is 0.03 here, you get 6 plus 1 by, if you just simplify, you are going to get 1 by 400, and you can see that this is equal to 6.0025. And as you can see here, again, this is really a great estimate that we are getting, because if you calculate the actual value of square root of 36.03 up to 4 decimal places at least in your calculator, you get 6.0024, which is to say that you have a great approximation. Okay, and let us see how great it is. So, let us look at the error that we have made, and let us calculate the Lagrange's form of the remainder here. The remainder is given by 1 by 2 factorial, the second derivative at c times x squared for c between 0 and x. Here x would be 0.03. So, the remainder term is 1 by 2 f double prime at c times x squared, and if you substitute for that, so you are going to get 1 by 2 times 1 minus 1 by 4, c plus 36 to the power minus 3 by 2 times x squared. So, this then gives us, if I evaluate the error term at 0.03, R2 of 0.03, I am going to get minus 1 by 8 c plus 36 to the power minus 3 by 2 times 0.03 the whole squared. Right. Now, as I was telling you earlier, why do we take the upper limit to the error? Because this error expression, the expression for the error that you have here is in terms of c. So, depending on the value of c, because c can take any value between 0 and 0.03. So, depending on the value of c, you will be able to understand how much is the error. So, this is why what we do is we just report one number, which is the maximum amount of mistake that we can make, what is the maximum error that we can make, and that is why we look at the upper limit to the error. Now, how do we find the upper bound to the error, the upper limit to the error? We know that c lies between 0 and 0.03, okay. So, this is to say that c plus 36, why am I doing this? Because see, the absolute value of the error is 1 by 8 c plus 36 to the power minus 3 by 2 times 0.03 square. Now, see, I do not have to, 0.03 square is a given number I can calculate, and 1 by 8 is also fixed. The point is, what the upper limit of the remainder would be nothing but the upper limit of c plus 36 to the power minus 3 by 2. So, that is why we are looking at these inequalities, because c lies between 0 and 0.03, c plus 36 will lie, just add 36 on both sides, you get 36 is less than c plus 36 is less than 36.03. And because I want to look at what happens to c plus 36 to the power minus 3 by 2, so I raise both all these expressions to the power 3 by 2, which gives me 36 to the power 3 by 2 is less than c plus 36 to the power 3 by 2 is less than 36.03 to the power 3 by 2. And then, because I want minus 3 by 2 in the exponent, I can I'll have to reverse the inequality, so that my upper bound c plus 36 to the power minus 3 by 2, the upper bound to that would be 36 to the power minus 3 by 2, which in turn gives me the expression here for the upper bound, because 36 to the power minus 3 by 2 would be 216, right? That's the upper bound. So I have the upper bound as 1 by 8 times 1 by 216 times 0.03 squared is 0.0009, and this, once you calculate the expression, the value for this expression, that's 0.0009 divided by 1728, which is then equal to 5.2 into 10 to the power minus 7. That's your upper bound. That's a maximum error you're making. That is also going into like so many decimal places. It's such a tiny error. So this is then how we handle the problems. In the context of Taylor's formula, you should be able to write down the Taylor's formula. You should be able to get any estimations that you're asked to calculate, and you should be able to give a sense of how good your approximation is by reporting the error, in particular the upper bound to the error. Now, one more example that you can try for yourself is where the function is given by 1 upon 1 minus x. You verify that the quadratic approximation is 1 plus x squared for x close to 0, and then determine its accuracy for mod x less than or equal to 0.1. So I'll quickly run you through this example, which is taken from one of the DU exams, Delhi University exams. Here in this case, f of x is 1 minus x to the power minus 1. The Taylor's formula for a quadratic approximation, the Taylor's approximation, the polynomial approximation, the quadratic one would be f of 0 plus f prime at 0 times x plus 1 by 2 factorial, the second derivative at 0 times x squared. And once you do once you find out your derivatives, the value of the function at 0, you get f of x is approximately equal to 1 plus x squared. This is something which you should be able to do easily now. Now let's just take a quick look at the error term, which in this case would be 1 by 3 factorial, because now n is 2, so the remainder is r3 of x, which is 1 by 3 factorial, the third derivative at c times x cubed. So you can calculate these expressions on your own, and you will get r3 of x, once you do the calculations, as 1 minus c to the power minus 4 times x cubed. Okay. So this is the expression for the remainder. Now 1 minus c to the power minus 4, I can write as 1 upon 1 minus c to the power 4. Any function of this kind, a function of c, would be a strictly increasing function and would have the highest value where c is, because if you notice here, c runs from minus 0.1 to 0.1. The mod of x is less than 0.1 because c lies between 0 and x, so x lies between minus 0.1 to 0.1. So c also runs through the values minus 0.1 to 0.1, and you can check for yourselves that this fraction here, 1 upon 1 minus c to the power 4, it attains its maximum where c is equal to 0.1, and that then gives us the upper limit as 0.9 to the power minus 4, or 1 upon 0.9 to the power 4. So this we can then use to calculate the upper limit to the remainder, which is the absolute value of r3 of x, which is 1 minus c to the power minus 4 times mod x the whole cubed, and this then is less than 0.1 cubed, because mod x is less than 0.1. So instead of mod x cubed, I'll have 0.1 cubed divided by 0.9 to the power 4, and this is 10 divided by 9 to the power 4. This is all we have for this part of the video. Thank you very much.